Hello, everyone. In this section, we are going to be discussing the binomial distribution. So let's go ahead and get started with, well, what the heck is the binomial distribution? So the binomial distribution is a distribution which consists of the following properties. So we have a discrete probability distribution with a fixed number of independent trials. Now it has these properties. It has n, so you have some predetermined amount of identical trials. Each trial must be independent. For each trial, there are two outcomes. For the purposes of just how we discuss them, one of them is called success. Now, the success might be bad, but it's what we're testing, okay? The other is labeled as a failure. The probability of success is P. The probability of a failure is 1 minus P. Now, some textbooks, instead of just leaving it as 1 minus P, some of them call this Q. So if you see Q, that just means 1 minus P. The binomial random variable X counts the number of successes in n trials, and the mean is NP, and the variance is NP times 1 minus P. Again, you'll also sometimes see this written as NP. Q, where again, Q is 1 minus P. Okay. So how can we make use of this? Well, let's go ahead and take a look. Consider the experiment of tossing a fair coin 58 times. How many times can we expect to get heads? Calculate the standard deviation for this distribution. What does that tell us? So let's just double check to make sure this is a binomial experiment here. So we have a fixed number of trials, 58. Each of those is independent. Flipping a coin heads on one does not affect whether or not it's heads on the other. There are two possible outcomes, heads and tails. The probability of success is given. For the random variable, it's in n trials, in this case 58. And then we have this formula here. So how many times can we expect to get heads? So for this, we're just going to go ahead and make use of our mu equals NP, which is 58 times 0.5. So we get that there are 29 times that we can expect to get heads. The standard deviation, now if the variance is NP times 1 minus P, then the standard deviation is the square root of this. So NP 1 minus P. In this case, it is the square root of N, 58, P, P is 0.5, and then 1 minus P is also 0.5. And then we take the square root of this. So I take the square root of 58 times 0.5 times 0.5. And we get that this is approximately 3.8. Okay. So we would expect to get 3.8 for our standard deviation here. Okay. So it's not unusual or unexpected if it's 3.8 more or 3.8 less. Okay. Now, if we want to find the probability that we get some number of successes, that is to say the probability that our random variable X occurs X times, this is given by N, choose X, where this is the number of successes we're looking for, times the probability that it occurs to the Xth power times 1 minus P, or Q if you prefer, to the N minus X power. Okay. Now, this is what the formula is. In general, we're not going to make use of this. We'll just make use of our calculators for it. But let's go ahead and just make use of it so that we can show that we are able to do so. What is the probability of getting exactly 6 heads in 10 coin tosses? All right. So this is the probability of X equals 6, which is going to be N. So we have 10 tosses. choose 6 of them. By the way, this n choose 6 here, or this n choose x, this is so we know which of them it's going to occur. So it could be that like it's choosing which of the 6 of the 10 is going to succeed. So that's why this n choose x is important here. Times the probability of x, 0.5 to the 6th power times 1 minus 0.5. Well, 1 minus 0.5 is 0.5 to the n minus x, 10 minus 6. So I get 10 choose 6. Which is 210 times 0.5 to the 6th times 0.5 to the 4th. Incidentally, if you want this equation to kind of make sense to you, it will be this to however many you're looking for, and then 1 minus this to the whatever you need to add to this to get to this. Okay. So 6 plus 4 is 10. So that's why you know it's going to be 4. Anyway, so it's going to be 210 times 0.5 to the 6th times 0.5 to the 4th. And we get approximately 0.2051 for our probability. Okay. Now, if we wanted to do this instead by making use of a calculator here, then what we can do is we can go to stat. And then give me just a second to find it here. Yeah. So we go to our distribution menu here, and we are going to be looking for our binomial. Now, here's PDF and CDF. I just want to mention what the difference between a binomial PDF and binomial CDF is. So what the binomial PDF is it's going to be an input of X, and it will actually be the number of trials you have, the probability, and then X. Okay, so the number of trials, the probability, and X. This is the probability that X equals X. For CDF, this is going to be the same thing here, NPX, but this is the probability that X is going to be greater than or equal to, or is less than or equal to X. Okay. So here, in this example, I'm going to be making use of my PDF because I want to know if it is equal. So binomial PDF, number of trials that I have. So here, oh, actually, in my previous version of the TI-84, you just had to enter the string. But here they make it nice and easy for you. Anyway, so the number of trials here, 10. Probability, 0.5. X value, this is the number of successes, 6. It enters it there for you. Okay. And we get the same thing that we found. So again, where do we get that? You go to second, and then above this variables button is distribution. And then you'll want to go down to your binomial distribution. Okay. So then let's do another one. A quality control expert at a large factory estimates that 10% of all batteries produced are defective. If he takes a random sample of 15 batteries, what is the probability that exactly 2 are defective? Now, if we wanted to do this by hand, we could absolutely do that. We would simply make use of our formula here. Okay, so it'd be 15 choose 2 times 0.1 to the second power times 0.9 to the 13th power. Multiply those together. I'm feeling a bit lazier though, so I'm going to go ahead and I'm going to go to my distribution. I'm going to go down to Binomial Pdf because I'm just looking for exactly this many. We have 15 trials. Probability is 0.1. And I am choosing for defective to be my success case here. Note that if my probability of defective is 0.1 here, then I choose my success to be defective. If you chose your success to be not defective, then your probability would actually be 0.9 here. So be sure that you are consistent with what you choose for your success case to be, okay? And my X value, I want there to be exactly 2. The probability is going to be equal to approximately 0.2669. Okay. And that's it. Let's do some more. All right. So same basic example here, but this is going to be slightly different. A quality control expert at a large factory estimates that 10% of all batteries are defective. Takes a random sample of 15. What is the probability that no more than 2 are defective? So this is different than our last one. Our last one wanted to know the probability of 2 being defective. This one wants to know the probability of no more than 2. And this is where we start to see why we make use of our calculators here. Because if we wanted to do this by hand, we would need to determine what is the probability that none are defective, 1 are defective, and 2 are defective here because it's no more than 2. And then we would add up each individual one. So we'd be making use of 3 different uses of the formula, and then we add those together. Doable, but more work than I would like. So I'm going to go ahead and use my distribution here. When it is no more than or at least, we're going to use our binomial CDF. Now, if it's no less than, or if it's the amount that's greater than, you're going to do 1 minus that. Okay, so if you're looking, if it were, say, if how many are more than 2 are defective, in that case, it'd be 1 minus that. Okay. So here, binomial CDF trials, I am looking at 15, probability 0.1, and then my number of successes 2. So what is the probability that no more than 2 are defective? 0.8159. Okay. And there we go. Just making use of our binomial calculator here. Let's do another one here. What is the probability that a salesperson gets a sales call no more than 2 times in 6 sales calls if the probability that the salesperson gets a call on any given sale is only 50%? Assume that the one call resulting in a sale is independent of another call resulting in a sale. So let's just double check. Is this binomial? 6 sales. So we have some number of trials. We have some number of desired successes. We have the given probability of success, and all of them are independent. Looks like we've got a binomial distribution. We can make use of our binomial formula. Okay. So we want to know, find the probability that a salesperson gets more than 2. So here, more than 2. This means we want to know the probability that X is greater than 2. Now, remember what I said. If you're using our CDF, that tells you less than or equal to. This is greater than. Greater than is a relative complement to less than or equal to. So what I'm going to do is I'm going to do 1 minus my binomial CDF. Okay. And again, we're doing the 1 minus here because This is greater than my binomial distribution does less than or equal to. Okay. So I'm going to do 1 minus binomial CDF. So I have 6 calls here. Probability is 0.5 and 2. 1 minus this probability here is 0.65, 0.6563, rounded to 4 places. Okay. Now, if you didn't do this and you just put in the binomial CDF, what you'll find is that you get this here, but don't forget you have to do 1 minus this because it's greater than. Okay. Let's do another one. All righty. Suppose the 20% of programs sold at the home games of a professional sports team during the course of one season contain a special discount coupon. If all 8 friends in your group bought programs at one game, what is the probability that at least half of your friends received the discount coupon? So we have 20% sold at the home games. 8 friends bought it, at least half. So we want to know greater than or equal to 4 here. Okay. Make sense? All right. Now, we have to be a little careful here. You have to be a little careful here. Okay. So when we are looking at let's just double check here. If all 8 of your friends group, what is the probability of at least half? Okay, so we want 4 or more here. So what I'm going to do for this is I'm going to note greater than or equal to 4. My complement is going to be 1 minus the probability of x is less than or equal to 3. Okay. Because I want this, or rather, I should flip the direction here. Because it needs to be at least half of our friends. So we want it to be greater than or equal to 4 here. Okay. So this is the same as 1 minus, and let me note why this is true. So we want to know the probability that x is greater than or equal to 4. Now this is the same as 1 minus the probability that x is less than 4, because if you recall the greater than or equal to complement of less than. Well, if I look at less than 4, this is going to be the same thing as 1 minus the probability of x is less than or equal to 3. Okay, hopefully that makes sense. Apologies that my explanation was a little murky at the beginning there. So now, what am I going to do here? Well, first, this seems to be a binomial distribution. So I'm going to go to distribution, binomial CDF, and I'm going to have number of trials here, 8. Probability of success, 0.2. X value is 3 here. So 1 minus this, and I get 0.0563 is my probability. And there we go. Okay. Hopefully that makes sense to everybody here. Let me know if you have any questions or want to see any extra examples. Otherwise, I will see you in the next video.